liquid. How do you know it is a liquid? Because you can see the particles are gliding over each other, vibrating a bit, gliding, then they become, here when they make like a circle like that, a ring, we call it a ring, it's actually a bit of ice. So it's ice, water, so it's not a gas particle just yet. Okay, can you see there the pressure is 0? Because pressure is when you have a gas and it collides against the side of a container. Now, how can I change this water into a gas? Don't overthink it. Easy peasy. Water into a gas. Oh, it's a face. Say again?
What?
No, not the process. How do I turn it into a gas? What do I do? Water to a gas. You heat it up. You make it warmer. Yes? Was that somewhere in your brain? Not at all. We have problems. Okay. So, when I heat this up, you can see the gas particles. They glide over each other nicely, and now they start to move very, 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 very fast. And there you can see is our first particles that starts to evaporate. Okay. So I'm making this warmer, 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 warmer. You can see there a pressure is starting to form because it's the gas particles that exert a force on the size of the container. And there you can see most of the particles are now a gas. Yes? Okay. So now, I just want to keep it there. So now, all the particles are gas particles. They're colliding everywhere. Now I can start with my gas formulas. Pressure P1 V1 equals P2 V2. Yes? Okay. Now, how do I make the pressure increase again? What do I do to increase the pressure? Yes? Decrease the volume. Okay. So let's decrease the volume. You can see there the pressure increases. Can you see that? Pressure increases, pressure increases. I'm just waiting for the particles to cool down a little bit. I hope it's not going to explode now.
Can it explode?
Say again?
Can it?
It can. Ooh, there it goes. Return lid. Okay. What I want to show, okay, there you can see they are gas, all gas again, moving, moving, moving. Okay, yeah, it's gonna pop again. I want to show something, but it doesn't want to work that nicely. Okay, you can see that if you close the volume, the temperature goes up, there's higher pressure. But what I want to show you... is somewhere... when the particles are pressed very closely together, okay, then where does it say that?
At the pressure. You see?
Where? I think it's folder. I just want to show you how the particles move. I'm cheating a bit now. Okay, you can see I'm making it colder as well, so the particles are supposed to move slower and slower and slower, steadily. Okay, what type of phase do we have there? We can have more than one phase, but what phases will you find there? Solid, liquid, gas? Anyone? You will have, you can see some particles still move very fast, so it will probably be, some particles will be gases, but some are close together, they're not moving that fast, some of them will be a liquid, right? So here we have gas particles and liquid particles. So because we made the volume smaller, because we increased the pressure, some of the particles will be so close to one another that it will form a liquid. Will our gas laws still apply there? No, because it is a liquid and our laws are gas laws. So when you increase the pressure too much and the particles are too close together, then our gas liquefies. We say the gas liquefies. So it's not a gas anymore, it's a liquid, and our gas laws do not apply. So it won't act like we think it should act. Okay, now, at the beginning of grade 10, I told you, science is not black and white. There's not 2 plus 2 is equal to 4. It is 2 plus 2 is equal to 4, except if the 2 is sometimes a 1, then it's not a 4, then a da. You've experienced that, right? Where I say this is the rule, but then there's exceptions to the rule. Yes? Okay? Now the same thing here. We have gas laws, but they only apply if the substance is a gas. If it changes to a liquid, then our gas laws do not apply anymore. And if we have a gas, we can't make the volume smaller until there's nothing, because then where's the gas? And before it's nothing, it will have changed into a liquid before there's nothing. Okay? So our gas laws only apply to a certain extent. Our gas laws are actually made up for the perfect gas, the ideal gas we call it. Now the ideal gas does not exist. It's like the ideal teacher. The ideal teacher is strict, but not too strict. They are kind, but they are also a bit like on your place. They do not give enough homework, or do not give too much homework, but they do sometimes give homework because you do need to practice it, and they explain everything nicely, but they also do not talk too much or too fast. And Do you get a perfect teacher? No, you don't. You don't get a perfect teacher. You can't, like, every student can't like me, and that's fine. Okay, the same thing, you don't get a perfect student. You get very close to perfect students, but you don't find a perfect student. Same thing with gases. You don't find a perfect gas. A gas that always obey all the gas laws and always act like we think it should act, and. The ideal gas does not exist. There's gases that are close to it. The noble gases are very close to being the perfect gas, but it's not perfect. Okay, so that is why sometimes we talk about real gases and ideal gases. Ideal gas, the perfect gas that does not exist, and the real gas that behave like the ideal gas, and then at a certain point, not anymore. Okay, so like here, at a certain point, it's not a gas anymore, it changes into a liquid. Okay, so at your notes. Ideal and real gases. It says, an ideal gas is an imaginary gas. Tato, what is an imaginary gas? What is that? Is your imaginary friend in the class today? It doesn't exist, it's a made up. Okay, so an ideal gas is an imaginary gas that obeys all of the gas laws under all conditions. So it's always a gas, and it always acts like it should. And then ideal gases differ from real gases. Real gases are like oxygen gas, nitrogen gas, carbon dioxide gas, helium gas. Real gases are real things. So the ideal gas differ from real gases when? Oh, why? 2 reasons. Number 1, because the molecules possess mass but no volume. So this here is for the ideal gas, the imaginary gas. Plastic bag is not the bag anymore. So here I have a plastic bag. Okay. I fill it with air. Like that. Now it says there, if this was an ideal gas, perfect gas, then it has mass. So if I put it on a very, very sensitive scale, it will weigh no mass, but it has no volume. Okay. So if you read further, it says the ideal gas can only occupy volume as a result of its motion. So because the particles move around, they take up space, and can therefore be compressed until it occupies no volume. So it says if this was a perfect gas, then I can make this volume smaller and smaller until there's nothing. Is that possible? No. That is why the ideal gas is an imaginary gas, because we know it's not possible. If I do this, in some way, I can't make it any small. You all want me to pop it, right? Yeah. Right. So, very important there that you can compress it until it occupies no volume. So if we have to draw it on a graph, then I can take it, don't worry too much about what is writing there just now. Then I can make it smaller, 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 until the volume is 0. Okay, we know that can't exist, but that's the imaginary gas can go until it's 0. Then secondly, how does it differ, the ideal gas from a real gas? Is there's no attraction forces, no intermolecular forces. No attraction forces, no intermolecular forces between the molecules of an ideal gas. So it means even if you make it very, very small, the temperature, or if you make the pressure very, very, very high, then it will not liquefy. So real gas will liquefy, will become a liquid, where an ideal gas will not liquefy. Chop? Is carbon? Carbon dioxide. Shawnee? Of everyone, you should have paid attention the most because you don't have notes in front of you. The ideal gas, does it exist? No. So carbon dioxide, that does exist. It's not an ideal gas. Okay. So, it says there, real gases will behave like ideal gases. So, real gases, carbon dioxide, oxygen, nitrogen gas, all of them will behave like the perfect gas, when the pressure is low and the temperature is high. Okay, so it's like you guys it's like the teacher, I don't know. It's like the teacher, if the students give the perfect environment, then the teacher is perfect. No? And then when they do not behave like they should, then the teacher becomes imperfect. Not? Okay. Sometimes not. It's just a story. Okay. So, when we have special conditions, high temperatures, low pressures, then real gases do behave like ideal gases. Okay? But if we have high pressures and low temperatures, real gases will liquefy. They will become liquid. So, when we have high temperatures, low temperatures, real gases will liquefy, will become a liquid. And then I tell you the dotted lines in the following graphs indicate the deviation. Deviation is where it goes off the path, off the way they should behave. The deviation in behavior of real gases versus ideal gases. Okay, now this is the graph of Boyle's law, right, that you're going to do in your practical. You know, I've told you what you write on in your practical? And in your test? Yes, I did say quantitative aspects of chemical change, endo and exothermic graphs, redox reactions, acids and bases, and this chapter. 150 marks. The practical is just this chapter. Okay. Alright, so we have pressure versus volume. Now I'm going to read the graph from right to left. If the volume is very big, then the pressure is very low. So again, if I take this here. Okay, so if the volume is very big volume, then the pressure is not high. You can see it's not high at all, right? But then if you make the volume smaller, then what happens to the pressure? The pressure goes up, right? So the pressure, I think there's a hole in here. No, it's not. Okay, the pressure increases until a certain point. Then I can't make the volume any smaller, right? You saw that in this thing here. Until a certain point, I can't make the volume any smaller, and then it pops, right? So the same thing here. Until a certain point, and then our real gas, an actual gas that exists, the volume can't go smaller. The volume will stay where it is. So there we have the dotted line is where a real gas will deviate, will go off the path than what an ideal gas is. Because an ideal gas, the imaginary gas, we can make smaller until it's zero. The real gas can't. Okay? Or here we have volume, here we have 1 over volume. So this is making the volume smaller. So it looks like making it bigger, but it's not because it's 1 over V. Making the volume smaller until you can't do it anymore. So it says here at the bottom, molecules of real gases occupy volume. They do have volume. And then under high pressure, they lie next to each other and cannot be compressed any further. You can't make it smaller. Therefore, the volume of a real gas is greater than the corresponding volume of the ideal gas.
What's the point of making an ideal gas then?
No, it's just like we need to have laws to have formulas. So say right, under special conditions, real gases will obey these laws. That's just all. Yeah. So okay, a little bit of confusion. All right. So here we have pressure versus time. Volume versus not time, temperature, and volume. Oh no, this must be pressure versus temperature. Okay, so here, if we make the temperature smaller, so if you make the temperature smaller, somewhere a gas will condense and it will form a liquid, right? And can we compress a liquid? Claudia asked about that. Can I take this liquid and compress it into this? No. So somewhere where, if you make it colder, the gas becomes a liquid, and a liquid, you can't make the volume any smaller. But if it was an ideal gas, it will never form a liquid, and you can make it smaller until it doesn't exist. Okay? Here, if we look at pressure, again, if you make it colder, somewhere it will form a liquid, and a liquid exerts no pressure, zero pressure. Because what is pressure? It's the collisions of gas particles against the side of the container. Okay, so it says there, at very low temperatures, the kinetic energy of the gas decreases and the molecules move slower and closer together. With real gases, the attraction forces, the intermolecular forces between the molecules, causes the gas to liquefy, to become a liquid, and thus occupy volume but exert no pressure. Alright, so here I will give you like a question like we did yesterday. These questions. And I will say, all right, now we make the pressure so much. No, now we make the volume so small. Let's say 10. And you calculate the pressure and you see the pressure should be, what was that? A kwart van 400. You see it will be 1,000. Okay, should the pressure be. And then I'll tell you, we did this experiment and now we see the pressure is not that. The pressure is less than that, or more than that. Why or how can that be? Then you're going to say, with the real gases, when you make the volume so small, the particles will be close together, there will be intermolecular forces, thus it will liquefy and not exert the pressure. Okay, so it will be a theory question like that. Okay, so what we're going to do now, I don't think we're done with the work, so you'll have off. That's not science. What we're going to do now is I'm going to hand out a question paper from last year. We're going to do past paper questions, and then we're going to mark that tomorrow in class. Okay. Grade 11, it seems that I've misplaced that question paper. Don't worry, I'll copy it for you now. I'm going to put it on the board, that question paper that I want you to do. Okay, you can keep that one because we're going to use that next term. Okay. So you can write there September 20. Thank you very much. September 2023 in your book. How many people have not received this question paper now? 1, 2, 3, 4. Okay. September 2023. Question 7. Okay, and you can start there. 2. Yes. Sst. Go. Het jy al neergeskryf? Or not, while I quickly go to copy list. If the learners are done